Hello, my name is Andrew Maselli, and I will be discussing a surface modification study on all additively manufactured materials, specifically looking over the residual stress effects applied to these materials and how these modifications alter the material properties. So, stress in thin film development is a topic of engineering that is apparent in many applications and can cause early failure in parts without proper accommodation or adherence to these properties. This post-process modification typically can help the material by mitigating defects at the surface and helps improve material properties such as hardness or strength of material to help reduce the effects brought on by extended use, such as fatigue of the material or wear down. So the form of manufacturing process, when looking at method, tools, and post-processing, can be one of the most important design aspects to keep in mind during the product development cycle in today's industrial environment. When creating a final design in standard manufacturing process, the differences between subtractive and AM materials there can be quite a few to be considered for the design specifications. First, looking at waste created during each process, we find that AM materials produce much less waste than subtractive manufactured materials due to the alternate post-processing that are done between these two. AM also allows for much more complex geometries than subtractive manufacturing, since the subtractive methods are limited to solid block, forging, and cast when creating the materials, whereas this additively manufactured process allows for a layer by layer creation of the material. And then finally, as a consideration, the AM materials are progressing with the number of materials that can be used in this process, but still are limited to being most suitable for materials with low melting points, such as polymers. However, materials with higher melting points, such as metals like stainless steel, titanium, nickel, etc., can be created in the AM method, typically by powder bed fusion or direct energy deposition, both utilizing powder as the raw material in their processes. The main consideration then for these materials are, do these contain the same material properties as their as manufactured counterparts, or is there a post-process step like one of the ones listed here in either the pre, intermediate, or post-processing that can be taken to get these material properties like these reference points for the wrought material or as-built material composition in a relatively simple process. So looking at additively manufactured materials, during the initial manufacturing process of additively manufactured metals, there are inherent pores and defects brought about by the conglomeration and the sintering of powders during the fusion of the material in an atmospheric environment. Vacuums or chambers filled with noble gases can help mitigate the trappings of these airs during the production, but even so, the defects and pores remain after build of the material is completed. These pores and defects then create an anisotropic material with more variability than the typical metal or plastic of similar composition produced in a normal manner, such as cast and die. Some of the defects on the left shown here include in the A, the gas entrapment, B, the lack of melt, C, lack of fusion in the process, and D, actually crack initiation that could occur just due to stress or thermal effects during this initial buildup process. And then I just have here on the right, a sputtering chamber, which would be relative to a vacuum chamber, which I'll be discussing later in the future, which we will be using to modify the surface by hopefully adding in a thin film growth and essentially building in that preferential stress as the hypothesis. All right, so just discussing a little bit on additively manufactured metals. They've only recently been implemented in the industrial world in the past 20 years or so, as compared to its counterpart, just the cast and die or subtractive manufacturing for the metals. And these metals are named so in additively manufactured due to their layer by layer addition, typically by the sintering or fusion of the powders. And they're able to form much more of the complex geometry models than that subtractive manufacturing of their similar composition metals. So this would be a much more beneficial process if the prices would decrease and if the material properties could resemble those of the subtractive or similar composition metals. So AM metals also produce much less waste during the manufacturing of the model and can be implemented much faster in a design process, as the model is typically formed from a 3D CAD model, then sent to the metal printer after slicing layer by layer by the software to manufacture the finished design. However, these AM materials have been proven by literature and studies to not stand up to the as-wrought similar composition counterparts. And actually, recent studies in literature have shown that the AM metals have a lower fatigue life and surprisingly an increased yield strength as compared to their similar composition as-wrought metals. And this has actually been theorized to be due to the creation of the aforementioned pores and defects throughout the material during the fabrication, caused by the layer by layer growth and the inherent defects associated with this process, and some thermal effects associated as well. Overall, the AM metals have a wide range of advantages and only a few disadvantages that as of today are becoming less and less prevalent as the AM technology improves, likely to see the process becoming an industrial standard in the next few years. And the fact that we can see a lot of variety is also beneficial, since these metal 3D printers today can be used in a personal and an industrial fashion with a wide variety of materials that is being added to every day. The metal printer allows for much stronger capabilities for the material designs printed due to the stronger yield strength inherent to the metallic bonding of the atoms. And the goal for our research is coating the surface of the material, this AM material, as a post-processing effect, introducing intrinsic stress effects, either in compression or tension, whichever will be the most beneficial coat for the post-process to increase the fatigue life and not decrease the yield strength in these AM materials to better resemble the as-built similar compositions. So this should also help in safety factors of design, along with increasing the use cases in many of the applications of personal and industrial use in large. And the PVD coating, or the powder vapor deposition coating, will allow us to create the coat by attacking the 3D printed material or substrate with the sample or the metal to be coated, using that vacuum chamber as mentioned before, or the sputtering chamber. And by controlling the deposition factors, or such as the deposition rate, we can thus control these intrinsic stress effects in the material. Literature also has shown that not much research has been done in this field, and the hope is that this technique could be a potential path to industrial integration as a post-process technique for a wide range of materials in the upcoming future. All right, so looking initially at uniaxial testing for these AM materials, we see that doing the elastic deformation during the elastic deformation, there's a lengthening of the specimen, but once we reach the plastic region, there is that unrecoverable necking occurring, which then leads us to the fracture points. By introducing a tensile or compressive stress at the initial surface of this AM material, we would like to see if the stress is becoming lower or greater due to this intrinsic stress effect. And just looking at current studies done for the additively manufactured material as compared to the wrought material of similar composition. This was a study done with an additively manufactured metal. It was found that the yield strength was greater in the additively manufactured material rather than its wrought counterpart. But as the strength increases, it does sacrifice ductility, and the fracture point occurs at an earlier point in the plastic region for the additively manufactured material. All right, and then moving into the cyclic range, we are now looking at the ratio of the minimum stress to the maximum stress applied in a cyclic fashion to the material, known as the R ratio, which can be better understood by looking at this as tensile stress applied as the maximum stress value, and the compressive stress then applied as the minimum over and over to the material within one cycle. And this is usually done in uniaxial for pure stress effects, but it can also be done in a rotating bending fashion to introduce shear stress as well. As this is an additively manufactured material, there will be some kinetic hardening that is occurring. That must be considered over the life of the material, and that can be shown on the right-hand side. So this one would be the broadening of the stress, and this would lead into some effects occurring in the fatigue life as compared to the regular sample. And as it has been known that fatigue is lowered in the AM metals, the theory now becomes, does this compressive or tensile stress, residual stress from the surface effect from the thin film coat, will it help this fatigue process? And does this change the kinematic hardening effect at all in the fatigue test? So as those are just some considerations, we will have to be doing some data later on, but this is one of the studies that was pulled from Dr. Simsiriwong's lab with fatigue life data generated from additively manufactured stainless 316 stainless steel and the same composition metal as built as well. We can see the difference in the two materials and how this kinematic hardening tends to reduce the overall fatigue life in the additively manufactured part. So this is now a consideration we must consider when trying to improve the properties of the additively manufactured part by hopefully increasing this fatigue life to closer resemble its wrought counterpart. And here, from the same study, we can see some crack propagation occurring in both the raw specimen and the additively manufactured material, and the inherent defects or the pores that are apparent in the AM material on the right-hand side at the microscopic level. All right, so how can we quantify this residual stress in the thin film that we create? Well, we would use Stoney's equation as a known example to find residual stress effects for thin film coats. And since we know that additively manufactured metals are created via the thermal heating and subsequent cooling in the material, there's actually a thermal gradient here during the buildup. So some of that thermal effect could already be there. So we would need to check the stress effect, residual stress effect of the material prior to the coat and then post-coat as well. Since this is considered a nonlinear anisotropic material, and there could already be some of this inherent residual stress inside. But Stoney does consider the tensile stress or the compressive stress apparent due to this film that we'll create. So he uses an equation listed here on the left-hand side to look at the surface stress generated, where the R is the radius of curvature, E is the Young's modulus, E is the thickness of the thin film applied, and then we find this surface stress generated due to this thin film. And wafer curvature, as shown here up at the top, is the most common technique to determine the intrinsic stress effects brought into the material by the PVD thin film coating. And the goal here being to measure the curvature of the film with respect to its thickness. And so this process has been the technique of choice to measure both tensile and compressive stress induced, as well as the layer by layer introduction of the two types of stresses for specific applications. Possibly if you have a tensile compressive tensile, or compressive tensile compressive, or just any form of stress gradient in the surface here. So we either want to measure this in situ or post deposition. In situ being during the deposition process. We could figure out a way to measure that. A recent study done was using a deflection of an optical beam, and they were able to measure the curvature of the surface during the process, which could give us applications for the stress gradient rather than just having a pure tensile or compressive on the surface here. And then the study done under Sincerong's lab just looked at a couple different surface effects for these AM materials, or the additively manufactured materials. And we see here the fatigue life for the as-built AM material, the machine material, and the vibration finish material, all leading to longer fatigue lives at higher stresses. So a lot of these surface effects alone can have dramatic effects on the material's fatigue life, an aim that we're hoping to accomplish with the residual stress effects applied to the surface of the material in this process. And this is just a study I completed on the surface modification that was submitted to SOARS this year. Basically, we just did an FEM model, or a finite elemental model, with pressure applied at all of the surfaces to resemble the thin film coat residual stress, and then did a uniaxial test to see whether this compressive or tensile stress changes the stress applied in any of the locations. And we found using the ABS, or the common 3D printed material, acrylonitrile, butadiene, styrene, we found that there was lower stress applied when doing a uniaxial tension test, and actually greater with the compressive stress applied to the surface. So in the post-processing of the model after fabrication, there are actually many different routes that we could take. So there could be the machines, post-process, and then the thin film coat, or the vibration finish, and then the film coat. But this is kind of going to be where we figure out what we move into next, since there are quite a few options here. And so it's our belief that preloading these models in either the tension, compression, or the stress gradient could reduce overall stress along the model, and then further increase the fatigue life or life of possible use of the material. And in this study, the overall or the average stress was then resulted from the simulation and extracted via the von Mises stress and compared between all of the sets. So after this initial study has been completed, we can see that the specific surface stress gradient could reduce overall stress throughout a model, and that the PVD coating preferentially deposited could be an optimal route for mitigating stress in the material. So it is now then our goal to expound upon a study by using real-life tensile testing to validate our results. We want to print out some ABS materials with the same dog bone pattern, and then thin film coat them with the preferential residual stress applied, either in the tension or the compression, and using the same stress strain. We want to see whether we get the same results here or whether the real life changes the results at all, most likely due to the anisotropic properties of both the materials. And then further research will be looking into 3D printing metals, thin film coating them, and seeing the effects brought on by the similar process. Then moving into the fatigue life of these materials with the thin film coat, and then afterwards doing some dynamic loading or loading that happens under a fraction of a second, impact tests, and seeing if the same post processes give us better results overall. And then at this point, an optimized process for the model and the loading case can be developed for the system. All right, and then so which one we'll be using? We'll be using the 316 grade stainless steel, since all the data was there. As mentioned before, we do have the fatigue life of the AM material and its wrought counterpart. And specifically 316 stainless steel is a common AM additively manufactured metal that's used in a wide range of applications across many different engineering disciplines, offering many case studies into the material for further inspection. And grade 316 stainless steel in general is an austenitic stainless steel with benefits of higher resistance to pitting and crevice corrosion in the chlorinated environments with excellent toughness characteristics due to this austenitic microstructure. So given the characteristics for this material, typical applications can be found in things like food preparation equipment, boat fittings, lab benches and equipment, as well as bearings for medical devices, due to each application needing some form of corrosion resistance and high toughness. We know that additively manufactured 316 stainless steel is a nonlinear material due to the aforementioned inherent defects brought about during the manufacturing process, and must be modeled as so during the analysis. So this process might be a little bit difficult, especially in the realm of finite elemental modeling, since these defects are on a relative microscopic level, as well as the thin film coat, since modeling this will require elements of very small size, since these thin film growths can be on the scale of nanometers to micrometers. So very, very small. And we know typically post-processing can improve a multitude of the issues inherent to this additively manufactured metal, including the surface modification and electropolishing that's been done to help reduce the structural defects and residual stress at the surface. But this is an ongoing study and research as of today. due to this complex modeling required to simulate each of these material characteristics. So overall, the additively manufactured 316 stainless steel is a viable material, given its anti-corrosive properties and inherent toughness for the biomedical applications, as well as other applications throughout industries. And specifically for the biomedical application, one specific benefit for this is that, interestingly, its at-raw design is used in the medical orthopedic implants, as the porosity of the additively manufactured metal of the similar composition resembles the porosity of the bone. It's aiming to replicate in its design, kind of increasing the osseointegration there. And the additively manufactured metal or the 3D printed metal could be easily fabricated to be person by person, rather than a standard part that might not be optimized for that specific load case or person that it's going to be implanted into. And that's all I have. Thank you for listening. Have a good day.